This is Nick and Caleb here. We're going to be looking at some interesting point distance estimation problems. So we have 2 points that are randomly selected and placed within a 1x1 unit square. Now D denotes the distance between these 2 points. The first 2 problems are relatively simple. Here we have the code for the expectation and the variance calculation. From this, we want to plot a histogram of the distribution of distances. Our next problem we're addressing is suggesting a more efficient method for estimating that the probability of the distance between the 2 points A and B is greater than 1.4. So this is, in simple, the probability that point A lands in one of the 4 corners and the probability that point B lands in the opposite diagonal corner. We're going to be zooming in onto one of the 4 quadrants to get a better representation of how to calculate this. Using Pythagorean theorem and the distance between the center of the square to the corner of the section that we want points to fall in, we can find some of the different distances and lengths of triangles and the sector. From there, we're going to calculate different areas.
So our next step is to find the theta of our arc that we're creating with 0.7 or half of 1.4 in this sector, and we use the law of cosines to do this based off of the dimensions that we determine, and we find that our angle is a little bit over 1 degree. With this, we're going to find the area of the sector in order to make our calculations, as well as the area of the 2 triangles that border it. So what we're going to do to find the area of the corner is we're going to subtract the 3 areas from the total area of the square. And in order to get our probability of all 4 areas, all 4 corners or sectors of the square, we multiply that times 4 to get the probability of 1 point landing in at least one of those squares. Since we are looking for the intersection of the event that it lands in opposite corners, the first chance is multiplied times 4 in order to land in one corner, and then by 0.001 to land in the other corner. So we multiply those together according to the rule of independent events in order to get our intersection, which is 4 to the negative 6. So we know by the rule of independent events that the following statistical laws hold true, and so there's 2 interpretations to this problem, and you can see the approximations that we have on the screen. And that's how we originally interpreted it, was that we have an equal chance at landing in any square or any corner, and then we have to hit the opposite corner, so that's 0.001. The interpretation 2 is to interpret it as a union of 2 possible events of landing in opposite corners. And so when we found this probability according to those rules, it was 0.000002 or 2 to the e to the negative 6. However, when we ran Monte Carlo 1 billion simulations, we found an error in our dimension of 0.001, meaning that Monte Carlo is also a very effective way to check your results, so make sure you're doing that. The resulting dimension should have been closer to 0.0002 in order to give us a probability to the order of a billionth.